When students understand the decade structure of the base 10 number system and are able to use that understanding to add 10 to any number within 100, they are ready to add one digit to two digits with regrouping. This stage provides a perfect opportunity for students to master the strategy of decomposition, or breaking a quantity down into two or more smaller parts. For example, suppose we are adding 5 to 7. We know that we need 3 to make 10 with 7, and 2 more to make 5 with 3. Thus, we have decomposed 5 into 3 plus 2. Doing so allows us to regroup or unitize 7 plus 3 to make a 10. We have shown that 7 plus 5 is the same as 10 plus 2, which is 12. Our understanding of decades should help us to realize that anytime we add 5 ones to 7 ones, we will get a similar result. For example, if we are adding 5 to 17, we know that we need 3 to make 10 and 2 more to make 5 with 3. Thus, we have decomposed the 5 into 3 plus 2, which allows us to regroup 17 and 3 as 2 tens, or 20. Thus, we have shown that 17 plus 5 is the same as 20 plus 2, which is 22. We want to guide students toward the understanding that adding one digit to two digits is exactly the same as addition within 20, with the added task of keeping track of what decade the answer will be in. Decomposition breaks this task down into two parts. The first part is what we need to make the next 10 and tells us what decade the answer will be in. The second part tells us how many ones will be contained in the answer. As we know, the MathRack number grid models addition in terms of numeration, or how many. When modeling adding one digit to two digits on the MathRack number grid, we are not asking students to use the commutative property. For example, when adding 8 to 44, we could take 2 from 44 to make 10 with 8. However, we are asking students instead to decompose 8 into what is needed to reach the next 10, 6, and the 2 that are left over. Thus, we want to show that 44 plus 8 is the same as 50 plus 2, or 52. Mastering the use of the decomposition strategy in this way is critically important because it will enable students to construct the meaning of multiplication and to become fluent with multiplication facts. If students do not understand decomposition, they are likely to take a finger counting approach to multiplication, which is not an adaptive or efficient strategy. Of course, we also want to model adding one digit to two digits in terms of magnitude, or how much. And this gives us a perfect opportunity to use the commutative property by finding the nearest 10 and using compensation to create a 10-friendly number sentence that is easy to solve. For example, what is the nearest 10 in the problem 23 plus 6? 23 is a distance of 3 away from 20, and 6 is a distance of 4 away from 10. Thus, 20 is the nearest 10, and we will use 20 to create a 10-friendly equation. We will use the strategy of compensation, or keeping a constant sum. For a review of compensation, see stage 7. First, we subtract 3 from 23 to get 20. Our knowledge of compensation tells us that we must then also add 3 to 6 to get 9. Thus, we have shown that 23 plus 6 is the same as 20 plus 9, which is 29. In this problem, 24 is a distance of 4 from 20, and 6 is a distance of 4 from 10. Thus, it doesn't matter which we use to create a 10-friendly equation. Either way, we will get 20 plus 10, which is 30. In this problem, 25 is a distance of 5 from 30, and 6 is a distance of 4 from 10. Thus, we will use 10 to create our 10-friendly equation by taking 4 from the 25 to make 10 with 6. This shows us that 25 plus 6 is the same as 21 plus 10, which is 31. As a practical matter, when adding one digit to two digits, decomposition is a sufficient strategy. However, we also want students to develop their understanding of compensation because they will need it to add two digits to two digits. We also want to continue to develop students' understanding of unitizing, or using digits to count groups of items as well as single items. We model unitizing on the 10-frame place value map. In this case, we have 4 10s and 8 1s in the 10-frame, and 2 loose ones. We are modeling the addition problem 48 plus 2. First, we move the 2 loose ones into the 10-frame, giving us 10 1s. Whenever we have 10 1s, we unitize to create 1 10. Thus, 48 plus 2 is the same as 5 10s and 0 1s, or 50. In this example, we have 9 10s and 8 1s in the 10-frame, and 5 loose ones. We are modeling the addition problem 98 plus 5. We can add 2 of the loose ones to the 10-frame to make 10. Notice that we now have 10 10s, so we must unitize the 10s to become 100. Now we add the remaining 3 loose ones, and we see that 98 plus 5 is 103. That is 100, 0 10s, and 3 1s.